Okay, so today's notes are on systems of equations, specifically solving systems of equations graphically. So our objective is to solve systems of linear equations graphically, and our language objective is to define terms associated with that, including system of equations, linear system, solution of a system, consistent system, including dependent and independent consistent systems, and inconsistent systems. So let's start by defining what a system of equations is. So our system of equations is a set of two or more equations. So it's any set of equations that has two or more, that would be a system. And so we're focusing now on linear systems because we've just been working on linear functions. So a linear system is, along those lines, a set of two or more linear equations. So a linear system is a system of two or more linear equations. And then the reason we're talking about these is because we're going to find the solutions of linear systems. So the solution of a system, or the solutions of a system, are a set of values for the variables that make all the equations true. So you're solving for a set of values for the variables that make all the equations true. So it's values that you can plug into any of the variables in the linear equations, and you'll get a true solution. Since we're talking about solving graphically today, this is going to be where the graphs intersection, or where they intersect, or their intersection points. So their intersection points, sorry, there's no need for that there. So their intersection points are going to be the solutions when we're looking at it graphically, because that's going to be the x and y values that work for both those linear equations. So before we go into more details about solving systems graphically, I want to talk about the different ways we can solve a system generally. So we can solve systems with, and there are four ways that we're going to, or there are four ways when we're solving linear systems. You can solve graphically, which we're learning today in 3.1. You can solve it algebraically with substitution or elimination. So these are both in 3.2. And we can solve it with matrices, which we're not going to focus on, but if you are curious, that is in section 3.6, I believe. Okay, but I can show you how to do that if you would like to learn at some point. So our next example, we're going to do super quickly. What is the solution of the system? And our system is negative 3x plus 2y equals 8. So that's our first equation, and our second equation is x plus 2y equals negative 8. So we're solving, since we're solving for the solution of the system, we're solving for the x and y values that we can plug in and make true equations for both of these equations. We're looking for x and y values that will make both of these equations true. And we're solving it graphically by finding the intersection point. So our goal is to find the point of intersection when we're solving it graphically. So the first thing I'm going to do so that I can graph these is, well, I'm going to graph them both. In most situations, you're going to probably find it helpful to isolate y or put it in slope-intercept form. So I'm going to solve for y in both these equations so I have slope-intercept form. So I started with negative 3x plus 2y equals 8. And I add 3x to both sides. I get 2y equals 3x plus 8. And I divide by 2 and I get y equals 3 over 2x plus 4. For my other equation, I started with x plus 2y equals negative 8. I subtract x from both sides and I get 2y equals negative x minus 8. And I divide by 2 and I get y equals negative 1/2 x minus 4. So those are my two equations. When I'm graphing both, I'm then going to sketch both graphs accurately. So this would be a lot better if we had graph paper. And we're going to do this until they intersect. So I'm going to do the best I can with what we have. So I'm drawing this graph. I know since this one has a negative and this has a positive intercept, I'm going to want to have room for both. This is my x-axis, this is my y-axis. Okay. Okay, so the first one, if I'm graphing this, I have it starts at positive 4, and it has a positive slope, so it's going up this way. So I'm going to go 1, 2, 3 over 1, 2, and down 1, 2, 3 over 1, 2, down 1, 2, 3 over 1, 2. And so you can start to see our line here. This is our first line right there. Our second line has a y-intercept of negative 4, 1, 2, 3, 4. So I'm going to start there, and it has a negative slope. So it goes 1, then over 1, 2. Goes up 1 over 1, 2. And so there I can see my intersection point. It's right here, this point, but I'm going to graph a little further just for good measure. So I have my full line that I can see. But the point is, this is our intersection point, and it is at negative 4, negative 2. So our intersection point is at negative 4. So my second step is going to be, so this was 1, 2. We're going to identify the point of intersection. And then we can check it by substituting into the original equations. So we're going to check this solution by plugging it into the original equations. So if I plug it into negative 3, and I have negative 4 for x, plus 2 times negative 2 for y, it should give me 8. So negative 3 times negative 4 is positive 12. 2 times negative 2 is negative 4 equals 8, and that is indeed true. So that equation checks out. Now I'll substitute it to the next one. So I have negative 4 for x plus 2 times negative 2 for y, and that should give me negative 8. I have negative 4 minus 4, which indeed checks out. So my solution is correctly negative 4, 2. The solution, I can write that as my final answer. The solution of the system is negative 4, negative 2. And that's our answer. Make sure you write down any questions, comments, concerns on that process. We'll do a quick check together in class, but there's one last thing I'd like to talk about with you guys. And that is consistent systems versus inconsistent systems. So a consistent system is one that has solutions or has a solution depending. And this is compared to an inconsistent system, which has no solutions. So consistent has solutions, inconsistent has none. And if we break off our consistent systems, there's two types that we can talk about. So when we're looking at consistent systems or systems that have solutions, they can be dependent systems. And these are systems that have infinite solutions. Or ultimately they are the same line. And this is compared to independent systems, which have one or limited solutions. So these are our two types of systems. We have consistent, inconsistent, and then within consistent, we have dependent and independent. So this is our little flow chart of systems. And then graphically, let's talk about what these different systems will look like. If we have intersecting lines, so if I just do a little sketch here, we have our X and Y axis. If I have a line here and a line here, they intersect once. So these have one solution. Therefore, it is going to be, I'm going to classify that if I'm looking at my systems up here, it's going to be consistent because it has a solution, but it's going to be independent because there's only one. So it is a consistent independent system. If I have coinciding lines, so again, if I have my X and Y axes, coinciding lines would just be one line on top of the other. So I have no great way of showing you this other than boldening this line, but coinciding lines just follow the exact same path. So there are infinite solutions. And so this again is consistent because there's a solution, but it's going to be dependent because there are infinite solutions for it. So look up at our definition, infinite solutions. And last but not least, we have parallel lines. So our last quick sketch. Parallel lines, we now have the same slope, different y-intercepts. So there are no solutions. They will never intersect. So it is going to be an inconsistent system. So we're just about out of time, but I'm going to have you guys do one quick check on your own. I'll write it here. I want you guys to determine if the following systems are independent, dependent, or inconsistent. So I'm going to give you two systems real quick. We have A, which will be negative 3x plus y equals 4, and minus 1/3 y equals 1. And then our second one will be 2x plus 3y equals 1, and 4x plus y equals negative 3. So try to figure this out on your own. All you're doing is comparing your slopes and y-intercepts to determine which of the following types of solutions you have. I'm going to go over it really quickly right now. So for the first one, I'm going to rewrite these both in slope-intercept form. So I'm going to add 3x to the other side. So I get y equals 3x plus 4 for my first equation. For my second one, I'm going to subtract x. So I have negative 1/3 y equals negative x plus 1 and multiplied by negative 3. So I get y equals positive 3 because I have negative 3 times positive 3, or times negative 1, sorry, is positive 3x minus 3. So if I look at these, my slopes, m1 is equal to m2. but the y-intercepts are different, so they're not coinciding, they're parallel because the y-intercepts are different. So B1 does not equal B2. Therefore, they are going to be inconsistent systems. So A is inconsistent. I'm going to follow the same process for the second set. So for the first equation, I subtract, and I have 3y equals negative 2x plus 1, and I divide by 3. I get y equals negative 2/3 x plus 1/3. And I do the same for the second equation. I subtract 4x. I get y equals negative 4x minus 3. So I move the 4x to the other side. This time, our slopes are different. So m1 does not equal m2. So therefore, they are going to be consistent independent because there's different slopes, different y-intercepts, so they're going to be independent. If you can't read that, I'll write it a little larger. Independent systems for the second one since they have different slopes. All right, that's all for now. Make sure you write down any questions, comments, concerns you have so we can go over them together in class.